Of all the weird and wonderful ideas to come out of science, perhaps the most weird and the most wonderful is quantum mechanics. Niels Bohr once said, anybody who isn't shocked by quantum mechanics hasn't understood it. Well, I'm certainly shocked by it, not to say completely nonplussed, even though I've only just glimpsed the surface of this bizarre subject. Paul Davies, in our last chat we were meandering among 100 billion suns. Let's now go from the macro to the micro. Let's look at quantum mechanics, the weird realm of the atom. Now abandon common sense, all ye who enter here, because once you get into quantum mechanics, nothing seems to make sense. But let's admit at the outset that the word quantum doesn't make sense to most people, and they get it utterly wrong. When lay people talk of a quantum leap, they imagine it to be something of considerable magnitude. The opposite is true.
Yes, that's right. The word quantum literally means package or packet, and it was first coined by Max Planck in 1900 because he discovered that light doesn't come in continuous amounts of energy, but in little packets or quanta. Those particular quanta we now call photons.
So a quantum leap is in fact what?
A quantum leap, in the case of light, is a very tiny discontinuous jump, say when light is emitted or absorbed.
Now I've hinted at quantum weirdness. Perhaps you might be kind enough to give us some examples.
Yeah, in daily life, of course, we're very used to notions of cause and effect, of things behaving in an orderly and predictable manner. When you get down to the microscopic realm of atoms and molecules, some pretty peculiar things happen, things that not only defy common sense, but they look to be just plain impossible. So let me give you a couple of examples of this. I have in my capacious pocket here a little ball. Imagine if that was an atom, or better still an electron. It would do all sorts of things that we would normally regard as impossible. Now, supposing I were to throw this ball at that window over there, then one of two...
It wouldn't have bounced back like that,
right.
would it?
One of two things would happen. Either the ball is going to bounce back or it's going to break the window and go through. Well, if that was an electron, it would be possible for it to pass through the window and come out the other side without breaking the window. In other words, it would, as we say, tunnel through and appear on the other side. I'll give you another example. Supposing I roll the ball along the surface of the table, and of course it drops off the edge. But again, if that was an electron, it's quite likely to bounce back off the edge. It's a bit like playing snooker, and when the snooker ball reaches the pocket, it bounces back at you. Now, if you saw that in daily life, you'd think that was just absolutely miraculous, totally impossible. But that sort of thing is happening all the time at the atomic level.
Paul, you're going to have to convince me that this sort of Lewis Carroll, Monty Python-esque weirdness is not simply a mind game played by the likes of you.
Oh, it actually has practical applications. You can make quantum devices. In fact, we're surrounded by them. All this electronic gizmos and things here use these quantum principles. In fact, when I was a student, there was something called a tunnel diode, which actually used the tunneling effect, like the ball going through the window, as a practical device. Maybe they still have them, I don't know.
What did it actually
do?
do?
The electrons tunnel through a little barrier inside, like a transistor, and it's an electronic component. But these days, the electronic devices that are built, fabricated at the level of individual atoms, all make use of these quantum properties. The fact that electrons can tunnel through barriers, appear and disappear, and be in two places at once. All of these things are put to practical use.
Paul, I'm trying desperately, but I remain to be convinced. Do you have another demonstration?
Well, actually, I've got one right here. Do you recognise this? It's an old-fashioned alarm clock. They won't let you buy it anymore because it's radioactive. It's luminous. It's coated with radium, I think. Makes it glow in the dark. And here we see the tunnel effect at work, because the decay of those radium nuclei involves particles called alpha particles, that Rutherford experimented with, that tunnel their way out of the radium nuclei. They couldn't get out if they were just ordinary common or garden everyday type particles, but because of this tunneling effect that we've been discussing, they can get out through the nucleus and fly off and deliver energy to the atoms around them and make the clock glow. So here we see the tunnel effect actually working. That is quantum weirdness before your very eyes.
And it's more reason to hate an alarm clock.
Yes, it rings a bell too.
Is quantum technology much use?
The ultimate practical device, which people are working on but they haven't yet built, is the quantum computer. We might actually have a computer that operates at the quantum level using quite different computational processes than your traditional computer, which is really sort of a clunk-clunk everyday type.
And the advantage of the quantum computer would be?
Oh, well, it could compute things that no ordinary computer could wrap its mind around. Let me give you an example, actually. It's a very famous one, the travelling salesman problem. You've got 50 cities and a travelling salesman that has to visit each one once and only once, and you have to work out an itinerary that minimises the distance travelled. It's a classic problem. You give that to a computer to solve. It takes a long time. You give it 100 cities, it takes much longer than twice as long for 50 cities. A quantum computer could probably crack that problem in pretty short order.
Why was Einstein a doubting Thomas? Why did he get cranky about quanta?
It's very curious because Einstein was actually one of the originators of the quantum theory. In 1905 he explained the photoelectric effect using the idea of photons. But in later years he came to hate the whole theory, and by the time he died he was very isolated and absolutely refused to accept that quantum theory was the last word.
He thought it was inelegant in a way, didn't he, or eccentric?
I think the problem was this. In the early days he thought it was just plain wrong, and he tried to think of imaginary experiments that would expose some sort of logical inconsistency. Well, his opponents always wore him down, and he conceded that there was nothing contradictory about the theory, in spite of its bizarre effects. So he retreated to a position where he said, well, quantum theory is right as far as it goes, but it's incomplete. There must be some other processes going on that we simply don't see at some lower level or some smaller level of reality. The thing that really bugged him about quantum mechanics is the uncertainty that's involved. Now, there's something called Heisenberg's uncertainty principle. Werner Heisenberg was one of the originators of the theory, and it says basically that there's a limit to what we can know about what is going on at the atomic level. I'll give you an example. There's a famous symbol, isn't there, for the atom? It's a nucleus and 3 orbits, something like this. Everyone recognises that as an atom. And I think most people have this idea that the atom's got a nucleus in the middle like the sun, and the electrons go around it like the planets going around the sun. So if you ask the question at any given time, where is the electron and how is it moving, we imagine that there must be an answer. Even though we may not have the equipment to see, we imagine the electron must always be somewhere and must always be moving in a certain way. Well, the uncertainty principle says that that isn't so, that it is simply not possible to say at any given instant where the electron is and how it's moving. You can have the one or the other. You can look very carefully and you can see an electron at a place, but then its speed is completely indeterminate. Alternatively, you can measure the electron having a speed, but then its position is indeterminate. So there's a trade-off.
This is a very exasperating notion, and I'm not surprised Einstein was irritable.
Well, it makes reality seem very slippery at the atomic level. It means that you can never pin anything down. There's a sort of fuzziness to reality at the atomic and subatomic level.
Paul, was this anxiety, this irritation, the sense of incompleteness what provoked him into saying probably his most famous single statement, God doesn't play dice with the universe?
That's right, because of course if you are uncertain about where an electron is and how it's moving, and if that uncertainty has got nothing to do with your technological limitations, in other words, if it's intrinsic to nature, if the electron really is uncertain in itself as to where it is and how it's moving, then it means you can't predict from moment to moment what is going to happen. See, again, in daily life we have this notion that if you throw a ball in the air or something, you can predict where it's going to land, and if you do it again, it'll land in the same place. In other words, nature is repeatable and dependable. But at the atomic level, you can set up identical systems in identical states, and they'll do different things. You can fire an electron at a target, and it bounces to the left. You can repeat the experiment with identical circumstances, and it'll bounce to the right. And all you can do is give the betting odds. You can say 50-50 to the left or the right. So quantum theory is basically a statistical theory. It's a theory like roulette or dice, where you can give the betting odds, and it's quite precise and mathematical from that point of view, but you can't say in any individual case what the outcome is going to be. And Einstein just hated that idea. He hated the notion that the future was indeterminate.
And if in a moment of sloth you don't look and see?
Well, then what you have to conclude, according to the rules of quantum physics, is that there are two possible worlds, one with a left-moving electron, one with a right-moving electron, and both of these worlds somehow coexist in a hybrid reality.
When you say something like that, as simply and matter-of-factly as you do, to what extent do you really deeply comprehend and know it?
Oh, I think I understand what is happening. That is, it's not a problem for me to imagine two worlds with two different things going on, projected on top of each other and overlapping. It's like taking two movies and projecting them onto the same screen.
Is it limited, however, to two, Paul? Does the theory not allow an infinity of
Absolutely
possibilities?
Right. In the more general situation, there are infinite possible outcomes of a scattering event or some other atomic process, and we must imagine an infinite number of alternative realities, or contenders for reality, superimposed upon each other, a superposed reality. And it's all less than real, in the sense that true reality, of course, only comes when we look and see, and we can be sure as to which of these outcomes has actually taken place. So I would refer to these contending realities, these alternative universes, as potential worlds, not actually existing worlds. But many
so
of my
each is not as good as the other? They don't have the same status?
Each has the same status, but it's only when you actually make an observation that you concretize one of those possibilities. Now, I have to say right here that many of my colleagues profoundly disagree with that. They believe that these alternative worlds are equally real and that they're really there as parallel universes. So if you fire an electron at a target, and it may go to the left or it may go to the right, the universe effectively splits into two, one with a left-moving electron, one with a right-moving electron.
Well, given that there are an infinite number of observations one could make, this means that there are infinite infinities
exactly right.
of alternatives, options.
A multiverse, we might call it, or an infinite number of parallel universes or parallel realities. It's called the many worlds interpretation of quantum mechanics. It's very popular.
Now, when I get disturbed, emotionally rattled, I sometimes feel the need for a pet. They're very soothing. So might we introduce at this stage Schrodinger's pussy?
Yes, cat lovers, please switch off now. Schrodinger had this thought experiment, it's never been done in practice, to show the bizarre nature that we've been talking about of these atomic processes on an everyday scale. Because, of course, I guess most people can accept that atoms are sort of weird little things, but seeing as you don't run into them in daily life, does it matter if something funny is going on among atoms? But if something funny went on an everyday scale, if we saw two contending realities in this room, we would find that very shocking. And so in Schrodinger's cat experiment, what happens is this. The pussycat is put in a box, along with a flask of cyanide and a hammer, and a triggering device that is set off by an atomic process, like the decay of a radioactive nucleus. Now, according to the rules of quantum theory, if you apply it to the entire contents of the box, including the cat, which is, after all, made of atoms, what you are to suppose is this, that if, after running the experiment, say, for 1 minute, there's a 50-50 chance that the atom would decay, trigger the hammer, break the flask, kill the cat, then if we don't look and see, if we don't actually open the box and see if the cat is alive or dead, we're forced to conclude it's in a superposition of a live and dead state. In other words, it's in a hybrid state of liveness and deadness, whatever that means. And it's a sort of reductio ad absurdum argument, because, of course, presumably the cat knows whether it's alive or dead, but it raises the whole issue about what does it take to prompt or provoke nature into making up its mind as to which of the contending realities it wants. Does it take somebody peering in a box, or does it take a cat, or could a computer or a camera or some simpler device, as it were, prompt nature into making up its mind? Well, there's no agreed answer to this.
But in what you're describing, nature doesn't need to make up its mind. Nature simply allows for every possibility.
That's right, but the question is, are all these possibilities really there? Are they coexisting in parallel?
Parallel universes, it's a mind-boggling notion, of course. Are you suggesting that there are universes in which Tony Blair lost the last election?
That's right, yes. According to the theory, if you subscribe to this particular interpretation, which many of my senior colleagues do, I might say, these contending realities are really there. In other words, quantum physics tells us that there isn't one universe, there's an infinity of them, and all of these different possibilities, all of the things that are possible at the atomic level and above, are really happening somewhere, not over there or over there, but in some parallel reality.
Are there Luddites who take an alternative view to this, who are hostile to this?
Yes. I would say that during my career, there's been a decisive shift towards this many universes view of making sense of quantum mechanics. So most of the senior figures in theoretical physics now would regard themselves as backing this many universes view. But there are certainly 4 or 5 other ways of interpreting what's going on. I can tell you what the party line is. Niels Bohr, who was the bit like the father figure of the early quantum theorists, he said, we have this everyday world, often called the classical world, of common sense, and then we've got this sort of madhouse quantum world down there, and somehow we have to interface the two, and where is that interface? And he felt that, that at some point, this peculiar quantum theory would have to go over into the everyday common sense world of classical physics. But he was very coy about what point and how it was that one lot of physics could turn into another lot. And today, I think most of my colleagues would say, well, if quantum physics is the correct theory of the universe, it's got to apply to everything, even the everyday world. And the fact we don't notice these peculiar effects occurring on an everyday scale is because...
I'm very grateful that we don't, Paul.
Well, we don't, except I should point out that it's not physical dimensions that count. It's going to be something more complicated, like the complexity of the system or its mass or something. We don't know. We don't know what it is that causes the quantum world to turn into the classical world. My own personal feeling about it is that these potential realities are not really real. That what happens is that when the quantum system that we're considering gets sufficiently complex, and I think a cat is complex enough, that it goes over into the familiar, everyday, common sense world.
Like the sort of a gravitational pull that destroys
well, I'm not sure it's gravitation. I think it is literally complexity. I think if the system is complex enough, the rules of the game change. But I'm in a minority of about 2 in taking that point of view.
But I've got a terrible feeling that another interview is being conducted in an identical room. We are taking a completely different position.
Well, that's exactly right. You see, so according to this many universes view, not only are there all these different realities, but they're inhabited by almost carbon copies of ourselves. So there will be another universe somewhere with a Paul Davies and Philip Adams having a slightly different conversation.
This raises the issue of the way the human mind is entangled in the ultimate reality of the cosmos, doesn't it? Because you're now dealing with our perceptions of it.
That's really the whole point. The really disturbing thing about quantum physics is it does seem in some way to take into account the observer. It entangles the observer and the observed in a very intimate way. You see, in the old-fashioned physics, in the classical physics, the observer was just there for the ride. In Newton's scheme, there can be observers, but they don't really matter very much. Now, of course, we all know that observers disturb the system they're observing. You put a thermometer in a glass of water, the act of putting the thermometer in is going to change the temperature of the water. But you can compensate for that. In principle, you can take all that into account, and you can make a measurement as accurately as you like. Quantum physics says that the very act of measurement will disturb the system that you are trying to measure in a way that can never be taken into account with any certainty. In other words, it enfolds or entangles the observer with the observed in a way that can't be untangled. And so this seems to bring in something like mind, something like observer, in a very intimate way. Now that's anathema to most scientists. And the retreat into this many universes interpretation is really a way of trying to evade introducing the observer at all, because you don't have to say that a cat is good enough or a human being is good enough or something strange happens when an observation is made. You simply say all these possible quantum alternatives are all acted out in their own universes in their own way, and they're all parallel realities, and everything that can happen does happen. And so it sort of neatly evades having to introduce the observer in a crucial way. But my feeling is it's a big missed opportunity, because any complete theory of the universe, and quantum mechanics claims to be a complete theory of the universe, any complete theory has to explain observers. It has to tell us why there are such things as observers and observations. And so it seems to me this is the one place we should be looking to actually explain the existence of observation and mind and so on. And to try to sort of define it away by having all these parallel worlds seems to me like a missed opportunity.
Could it be possible that at the moment of the singularity, at the moment of the Big Bang, there were alternative universes created?
Oh yes, that's right.
Where the maths didn't work out?
Well, all of this we've been talking about so far assumes that the mathematics is the same, that is, that there are underlying quantum laws, and that all that is happening, there are different alternatives which are available within the scope of those laws, all acted out.
Right.
And of course it comes into its own in this subject of cosmology, quantum cosmology. We apply quantum physics to the universe as a whole, and you might say, well, hang on a minute, quantum physics is about little things, about atoms, cosmology is about the universe. How can you apply quantum theory to the universe? And the answer is that the universe was once very shrunken. In the Big Bang, everything was very compressed to atomic dimensions, and quantum physics must have made a difference. Now the question is, how do we interpret it? Now, if you're one of these people that believes the observer matters, then that's a problem, because if you're applying quantum physics to the whole universe, you can't get outside the universe to observe it. It's everything there is. But the many universes people are fine, because they can just assume that all possible universes that could exist are all acted out in parallel. All possible things that can happen do happen. And so just as we see a universe like this, which is expanding from some initial singularity to an uncertain future, there will be another universe which would have not expanded so far as ours and would already be collapsing. There'd be another one that would be expanding much faster and would already be nearly empty. So all of these possibilities are there together.
Trying to contain these notions within your neurons and synapses must be a bit of a strain. How do quantum mechanics stay sane?
The one thing is, don't try to visualize it, you see. There is this perception, I think, among the public that if something can't be visualized, if you can't see it in your mind's eye, then it can't be right. I get people write to me, get quite exasperated and upset. They say, this theory can't be true because it makes no sense to me, I can't imagine it. But what is common sense has been honed by evolution. Darwinian evolution has equipped us to survive in the jungle, and we're quite good at jumping across rivers and catching falling apples and doing all sorts of other things. There's no reason at all why Darwinian evolution should equip us for understanding what's going on inside atoms, because they're just not relevant to surviving in the jungle. Same thing with black holes and curved space and all the other things out there in the cosmos. We find them hard to understand because there's no good evolutionary reason why we should. And that's the power of science. The great thing about science is that it can take us into territory where common sense is left behind.
Are you suggesting that science can take us beyond the reach of evolution?
It takes us beyond the reach of common sense. Evolution has equipped us for common sense and for visualization of, if you like, everyday states of affairs, things that have survival value. But there's no survival value in being able to visualize what's going on inside an atom. And yet we can still do it. And we can do it by using mathematics as our sure guide. So abandon common sense, or ye who enter here. I mean, that is the whole point, that you don't need to be guided by your intuition, by what seems natural, by commonsensical ideas, because they will lead you astray.
In our next exciting episode, we search the dark secrets of the universe.